Euler's method is a way for us to approximate the solution to something that we would otherwise need totally different techniques or just wouldn't be able to do it at all. Here we go. So I don't know if you picked this up from the intro video, but basically Euler's method is simply a series of little line segments that we use to approximate a curve. And so, did I draw any graphics on that intro video? Any like graphs of curves? Did I have a Desmos graph in there?
You graph the solution.
Oh, did I graph one of the solutions?
The points that we got from Euler's method.
Okay, so let me give you one other perspective because I would like you to see this. Don't write this in this space. I'm going to use this and then I'll erase it. Just want you to think about this. So with this first example we're going to do here, we're told over here that y of 0 is 3. So that's, like, say right about there. And then we are told that we got this differential equation, y prime equals y minus 1. And we're supposed to estimate 0.5 for the step size of 0.1. So what we're essentially going to be doing here is using little line segments. So maybe the first one would be based on the first point. So the slope is, well, let's see here. Let's actually figure this out. The slope would be 2, I guess, right? So we'd say first line segment looks like this. This would be 0.1. And then out here at 0.2, maybe we go slightly steeper. And then 0.3, maybe it goes even steeper. Maybe we start to see a little bit of a change. I don't think this is really true, but let's say that it were to like bend down this way a little bit. And then 0.5 would be out here. Let's say that looks something like that. I'm kind of making this up now. I don't think this is really realistic for this particular example. But you see, we just have these little line segments, and the line segments are supposed to mimic the shape of the solution curve. So I would say that the solution curve could maybe look something like this, where it would go up, and then it would come back down over to here, something like that. So the little blue line segments are going to be off from the actual solution curve. They're not going to be exactly representative of that, but they will be close. How close is close enough? I don't know. We could debate that, right? But we know that it's going to be an approximation. We know that it's going to be fairly close. Can you think of what strategy we could take? Like, what if we got to the end and we thought, ooh, that's not close enough? What strategy could I take to make my final answer a lot closer? Any ideas? Say, what about the step size?
Decrease it, make it smaller.
Yeah, make the step size smaller. So instead of 0.1, how about 0.01? So think about this, though. If I made the step size 0.01, instead of 5 steps to get to where I need to go, how many steps would I need? 50, right? I'd need to find 50 little line segments, and they'd all be closer to the curve than those are, but I'd need to do 50 of them. What if that wasn't good enough? What if I wanted to make my step size 0.001? Now there's 500 steps. Is this starting to feel like something that would probably be best suited for a computer? Yeah. For sure. And so for that reason, I'm never going to have you, I'm never going to say, hey, use 50 steps to approximate the solution, blah, blah. I mean, it's just a waste of your time. If you can do like 3 or 4 steps, maybe 5 steps, and demonstrate, okay, I know what to do. I would think for some of you that are good at programming, could then take those steps and create like a recursive action in your program and make a wonderful little program that would do it with whatever step size you wanted.
So you
right?
do another graphing calculator for the AP test?
Well, they have their ways of figuring out if you know what you're doing or not. Namely, this would probably be on the no calculator section.
Yeah.
But as far as being able to approximate the solution to a differential equation, yeah, why wouldn't you do that? You all know, I think you all know this, engineers are more interested in quick and good enough versus perfection, right? So if an engineer can get an answer that's within their acceptable error range and they can do it quickly, that's what they're going to do. And so this is kind of what that's geared toward. If you could just get something that's good enough where your error is controlled, okay, well, we can do it really fast. Yay, that's what we want. Save money, save time. That make sense? Okay. So how confident are you guys feeling about doing a problem like example 2? You've seen the intro video. Maybe you kind of worked that example a little bit. Are you looking at this thinking, I think maybe I could do this? Or are you looking at it thinking, I need to see this done one more time before I feel like I could maybe do one? One more time? Okay, let's do it. So if I was going to do this one, I don't know about you, but I would like to start off easy and work my way towards the more complicated stuff. And so I'm going to set up my x's first. I usually do this in kind of a table format. I'm going to set up my x's. My first one is always x sub 0. So that's my initial x. And what's my initial x for this one? Yep, it's 0. And I know, based on what I was asked to do, that I want to find y of 0.5. And so I need to work my way towards the x value being 0.5. But I have to do it in a specific pattern. Yeah, the h tells me how to get there. It's going to be plus 0.1 each time to get there. So x1 would be 0 plus 0.1, aka 0.1. And then I would just add that h value each time. And I can see that it's going to take me those 5 steps that we mentioned to get to my desired x value. Just thinking of common questions from the past. You will always be given the step size or information that you could use to easily get to that step size. That's never going to be something you just like make up out of nothing. Okay, cool. So then the y's are a little bit tougher. The first one's not. What's my initial y? 3. So that x0, y0 should perfectly reflect your initial condition. And then, of course, all the other y's are probably going to be different. They're going to be changing as we go through this. So the way that I like to think about this is not a perfect representation of what's really happening, but this looks an awful lot to me like y equals b plus mx. It's not really a b, it's a y value, but it looks a lot like that slope-intercept form that we are all so familiar with. And all the information that you use to get the next point is based on the information from the previous point. So you use the previous point to get to the next point. So here we go. To get to that y1, I would write 3 plus my m is going to be the slope based on the previous point. And where on earth are we supposed to get our slope? Differential equation tells us all about our slope.
So
it'd be 3 minus 1. Yep, 2. So slope is 2, and my step size is 0.1. So it's the previous y value plus the slope based on the previous point times step size.
Okay.
So from this, you would get 3.2.
Can you say that again?
Yeah, so all of this information, so this is, I'll erase this, but this is previous y value.
Mm-hmm.
This is slope based on previous point, because sometimes the x's will come into play when you're figuring out your slope. Like if your dy dx depends on y and x,
Right.
you might plug in a y and an x to get that slope, or it might, in this case, it might just be a y. And this will always be your step size. So you know.
Oh, I got you. Yeah. I see.
So basically, it's a b plus mx, and because the step size is like a little itty bitty change in x.
Yeah. But I was just tripping up. I thought it's all based on the previous point, basically.
Yep. All the
So-
information. The step size is going to be consistent, but all the other stuff is based on the previous point.
Okay. That makes a lot more sense.
Yep. What else?
That's what I was confused about.
So let's keep going. So I would say basically we have completed one cycle of Euler's method, and we need to complete several more to get to where we want to be. So my y2 is going to be completely based on the previous point, the previous set of information. So my y2 is going to start off with 3.2. That's the previous y value, plus the slope based on the previous y value. And what do you think that would be? 2.2, right? 3.2 minus 1. So 2.2, this is where this gets a little tougher, times the step size. What's 2.2 times 0.1? 0.22. So this would be 3.2 plus 0.22. I'm getting 3.42. So you can see the y values have gone from 3 to 3.2 to 3.42. So certainly creeping up, right? We're seeing an increasing pattern here as best we can tell. So y3. We start off with 3.42. What would be the slope for this one? 2.42. Yep, you got it. 2.42. And then, of course, we multiply that by the step size. So let's see here. This is 0.242. So I'm getting 3.662. Does that sound right? Okay. 3.662. Still seeing increasing pattern. And it looks like the y's are increasing at an increasing rate to me. All right. Y4. Do you see how this is very cyclical, right? Like, honestly, if you can do one of these or two of them, you can do all of them. You can do as many as you need to do. Okay, so the next one, Y4, is going to be completely based on what we had in Y3. So it's going to be 3.662
Plus 2.662 times.
plus 2.662 times 0.1. So again, y4 equals the previous y coordinate plus the slope based on the previous point times the step size of 0.1. Oh goodness, this is going to get tougher. So it's 0.2, I don't know. Anybody do this one yet? I don't feel like trying to.
3.9282.
3.9282? 9282? I knew there was going to be a carryover with the addition and didn't feel like doing that. Okay, so if you've done all these, you can do the fifth one and get to your final value, the one we're actually looking for. So this would be 3.9282 plus 2.9282 times 0.1. And again, please, if you could do the arithmetic there, that would be helpful. Hopefully a good final answer.
And it's always just going to be previous point plus the slope of the previous times the step size. Like it'll always be that format.
Previous y value
Yep.
plus slope, and like I said, based on previous point,
Yeah.
right?
Yeah.
Sometimes you'll get x's in your differential equation, times step value.
But it's always going to be that format.
Yeah,
Always.
every time.
Sweet.
So that's why I said if you can do it once or twice, you can do
Yeah,
it.
that's okay.
What
That's
did you
fair.
guys get
That's
for?
fair.
What y'all get for a final y of 0.5? 22102. You guys agree with that final number there? Okay. 4.22102. Okay, hang on. Thought maybe I'd show you something. That'd be kind of cool. Let's see here. I think a little zooming will reveal, as always, a little bit more. So when you zoom in a little bit closer, you can start to see how we are falling off of the curve, right? The first point is right on the money because we knew that was the initial condition. That is actually a point on the curve for sure. But every other point from there on out is going to be slightly underneath, right? That's because the slope of the red graph is positive, but increasing as well. So because the slope of the red graph is increasing, those blue points based on lines are always going to fall a little bit below. So hence our approximation would be a little bit underneath the actual value of the red curve. But you can see, I mean, I'm zoomed in here at this spot, I'm zoomed in to where, like, my scale on the Y's is in, 3.85, 3.9, 3.95. We're talking about in hundredths. And you have to zoom in pretty far to start to see a gap develop between the red and the blue graph. This would be where you'd say, is this error represented by this little bracket? Is that error acceptable? And this is where you'd have to make a decision. Maybe it is, maybe it isn't. If it's unacceptable, you do what Aiden said. You go back and make your step size smaller. And that would cozy it up there closer to the red graph. If that's good enough, you just leave it. What do you think? Kind of cool, right? I like it. Okay, cool. So then I think there's one more example to do. So if you would turn over to that one. And example 3. No, that was it? I'm so disappointed. Maybe we'll do another one. I wanted to do one more. I'm disappointed in myself. I should have put another one in there. I'm very disappointed in myself. Well, I'll tell you what. Maybe we'll wrap up class. We'll go. These are easy to make up, I think, for the most part. So we'll go back and do one of those. Okay? See if you remembered it for 40 minutes. Okay. And if you didn't, that's okay. So let's see here. Let's take a look at 6.2. And some of you guys were saying that there was a discrepancy between the intro video and this, and I'm okay with that. I think this is worth exploring. I think we have time to do that. So let's see here. Was this in there? Like a reminder of how to solve a differential equation?
Yeah.
This was in there? Okay. So let's do...
Examples on the video were, like your last example?
Like a specific example was different?
On the, bacteria?
There was a bacteria one?
Yeah.
Do they have just sugar and plutonium on this one? Okay. So let's do this. I think this is totally worth our while. Even if you watched the intro video and you saw this and maybe you knew how to do this or had seen this before, I think this is worth seeing again. And if you've never seen it, it's definitely worth seeing. So do y'all remember from pre-calculus about the exponential growth and decay, like PERT? And what did PERT actually equal? Interest. That's right. Principal times e to the RT. That would be if you had continuous compounding, right? So like it just going the whole time, which is unrealistic for a financial perspective. I don't think anybody would offer you continuous compounding on an investment. It would be pretty cool, but I don't think anybody's going to offer that. But yeah, so did you guys look at it from any other perspective other than the PERT thing? Was it always, you did?
CE to the KT.
E to the KT. Did you do just like kind of general growth as well, perhaps? Okay.
Bacteria.
Bacteria in a petri dish or something. It's pretty common. All right. So exponential growth and decay models, I would say A equals CE to the KT, as you mentioned. This is the most generic version of it. And of course, in your pre-calc class, it's probably presented as, hey guys, this is the exponential growth model, right? In here, we're going to go a little bit deeper. We're going to talk about where it comes from, why it is what it is. This is all based on the idea that you will get exponential growth from this. If the rate of change of the amount is proportional to the amount that's there. So in other words, the more that's there, the faster it grows.
Whoa.
Right? So that's why people joke around and say that bunnies multiply exponentially. If you have a field with 4 bunnies, a couple weeks later there's 8 bunnies. I think the gestational period of a bunny is about a month. That's from conception to birth.
Is it a month?
I think it's like 28, 29 days, something like that. So it's very fast, which is, if you think about it, really makes a lot of sense because don't bunnies have a lot of natural predators?
Yeah, that's fair.
I mean, coyotes, all kinds of birds, hawks. Say again?
Because I said they can't stop us all. It's a reference to the Area 51 invasion.
Yeah,
They can't
I don't
stop all
know.
the bunnies either.
Depending on how mean the bunnies are, right?
Yeah. Some
Yeah.
mean bunnies out there, man.
Yeah.
You ever seen The Lone Ranger? Those bunnies are mean.
I've seen Monty Python and the Holy Grail.
Ah.
One bunny may not be too bad, but if you give it a few months, then
Right, if there's a million of them, it's going to be tougher for sure. Yeah. So that's the concept here, is that the rate of change is going to vary with the amount that's there. The more that's there, the faster they'll grow. Not true of bunnies, but maybe other things it is. So here's the proof of this. What we would say is that y prime probably could be better written as dy dt equals k times y, where k is a constant, y is the population, right? It's how many bunnies are there, how many grams of sugar, how many kilograms of plutonium, whatever we're talking about. So we start there. How do we solve a differential equation? What's our first step? Got to do that. You got to do a separation of variables. So this would be dy over y equals k times dt. A lot of people get in the habit of thinking that if the y gets divided over to the left side, the k has to be divided over as well. The truth is it doesn't, and I think it shouldn't. I would leave the constant over there with the independent variable. I think that makes a lot of sense, because if you bring it over to the left, aren't you going to eventually later on have to bring it back over to the right?
Yeah.
So why do this when you could just leave it? Just saying.
I just need extra steps.
Yeah, let's make it as difficult on ourselves as possible. Yeah, sounds like our awesome philosophy. Okay, so then we do our antiderivatives. We get ln of absolute value of y equals kt plus c. And it's at this point we can probably say, if we're talking about the number of bunnies or the number of grams of plutonium or something like that, the possibility of the y being negative is probably not realistic, right? Because we're talking about the amount of things, like the number of gallons of such and such, or the number of bunnies in the field. We're not going to say that there's -5 bunnies, right? So if y is going to always be non-negative, I think we can say then that the absolute value of y will just be y. Based on that reasoning, based on what the initial condition would be, there's no way it's going to be a negative number. So then we solve for y by exponentiating both sides. So we get this y equals e to the kt plus c. And I got to admit, as over the years, having taught this many, many times, I feel like calculus students that have gotten comfortable with it have said, okay, yeah, separate the variables, antiderivatives, maybe we can handle the absolute value. This is the step where there's kind of like, I don't know what to do, some stumbles, maybe some mistakes.
I didn't know how you do that.
Yeah, so it's a question of how do I get what I currently have to look like this? Because it's kt plus c, and the c's up in the exponent, and all of a sudden it's not part of the exponent anymore, and no longer is it plus c, it's times c. The way that I like to think about this is, if you're adding exponents, what are you really doing? You're multiplying your bases, yeah. So you could split this up and say this is really y equals e to the kt times e to the c. It's taking that old rule you learned way back in Algebra 1 or something, and instead of multiplying the bases and adding the exponents, we take the adding exponents and split it up into the multiplying of the bases. We're just reversing it. And then the final step here would be to recognize that e is a constant, c is a constant. So some unknown constant as an exponent for a known constant just gives you some other unknown constant, right? So we'd more specifically write this as c e to the kt, where c is just e to some unknown constant. Technically, it'd be like a second c. We customarily write it like this just so we don't have a k for one constant, and then a c, and then a different c for the other two constants. You just customarily write it this way. So that's where it comes from a differential equation. You'll find out that's where a lot of things come from. Okay, how are we doing? You guys ready to deal with some radioactive sugar?
Yeah.
That's if you mixed the two questions. We'll keep them separate, I guess.
Oh, come on.
Speaking
Aye.
of sugar,
It'd be interesting. Oh, you know what, Peyton? I didn't even think about that, but this is a very appropriate question for you. So if you wanted to customize this, oh, by the way, how do you know whether you have growth or decay?
If it's
if K is positive.
If K is positive or negative, right? So K is positive, we have growth. K is negative, we have decay.
Oh, snap.
So yes, if you want to customize number 1 for Peyton and her problem, there you go. Sugar dissolves in water, or sugar dissolves in Peyton's stomach, something like that, maybe more appropriate, at a rate proportional to the amount still undissolved. If there are 50 grams initially, and after 3 minutes only 20 are left, that's the total time it takes for 90% of the sugar to dissolve. There's some tricky kind of wording to navigate through here, like namely the percents and undissolved versus dissolved and all that stuff. So see if you can navigate through this. I'll show you kind of what I would hope you would write in a question like this here in a
Do
minute.
we have to prove the equation every time, or
Well, that's what we're going to talk about. Like if you just want to start off with the
Is it only if they ask?
exponential growth decay relationship, that's fine. Yeah, we'll talk about the wording. You'll be asked to do it
Really?
at times. Like, well, maybe not in a situation like this, but you'd want to have the skills to be able to derive
Yeah.
that for sure. But as far as trying to be efficient with your time, we can certainly talk about that too.
Or you just use a line.
I'm involved in that. But hold that thought, actually. Can you? Yeah.
I just don't want to forget about it, so
Yeah,
I might as well
that's-
get it
Good idea.
done and turned in.
Very good idea. Good number 2. You all heard of that, the term half-life? Have you heard this, Aiden? If you were an AB before, you've heard of it, at least then.
Is half-life just looking for when 50% of the substance remains?
The time needed to get there.
Yeah, okay.
This is kind of the basis for how archaeologists will decide how old something is, right? Sometimes how much carbon is in the object will help them get a good idea of how old it is. Knowing what the half-life of carbon is and all that stuff.
Nick, just start plugging stuff in and you'll see it.
there's no C? C is the root of the time. Yeah, so 30% on
That's so cute.
So,
I like that. That's
second proportion. So, it says it is 70% back, right? And so let's say originally C is 10, and it's at 30% of the cost, we can do 7 after like 16 years, right? So you just do 0.7, because 7 divided by 10 is 0.7. Does that make sense? It's like just a proportion. And you just solve for 2. Does that make sense?
I know.
Yeah, we never know what C is, right? But we know the relationship between
You
the
get it.
amount and C.
Let's go.
Give me a high five for that.
You got it? You think you got this?
I think I got it.
Okay. Let's see how this went for you. See if we can all get a good answer. So I went ahead and wrote down my my differential equation based on this. Radioactive substance decays at a rate proportional to the amount present. So for this, it's the more that's there, the faster it decays. The less that's there, the slower it decays. So similar idea, but we're talking about decaying instead of growth. So if you wanted to, you could jump right to this and say R equals CE to the KT. And this is where this gets a little bit, I don't know, it's going to say awkward, but it's kind of cool the way this works, I suppose. So it says if 30, we don't know what C and K are, but it says if 30% of such a substance decays in 16 years. So if 30% decayed, what percent is there? 70, okay. But we have no idea what the C is, and we really don't know what the R is. We only know the relationship. So here's how I would look at this. I would say that R divided by C equals E to the KT. And if 30% has decayed and 70% remains, wouldn't R over C be 70%? So I would write 0.7 equals E to the 16K. You can see this will allow me to find my K value. So I'd go ln of both sides. This gives me ln of 0.7, all divided by 16 is equal to K. So I could go up here and I could write R equals CE to that K value times T. And then it says, what is the half-life of the substance? And again, to emphasize what Logan asked about, half-life units would be time. It's the time needed for the substance to get to half of what it was. So this time when I think about R divided by C, I will not be replacing R divided by C with 0.7. I'll be replacing it with 0.5 because I'm looking not for the 70% life, looking for the half-life. So 0.5 will allow me to find the half-life. Again, this comes down to doing a natural log of both sides and then doing a little division or multiplication, depending on how you want to look at that, and getting your T value. What would be the half-life? Did you figure it out? 31.09? 09 what? 4. So again, make sure when you're doing decimals, 3 decimals, sig figs. That's our rule. We always just go 3 to the right of the decimal. We don't worry about anything else. So you guys are all looking pretty calm on that 31.094 number? We all good? Okay, so I'm kind of excited. I think our class is over at 55, so this is good. I'm gonna call a little bit of an audible. So
Oh, audible.
yep, Blue 53, Oscar,
Hey, Manning.
Omaha, whatever.
Xerox, Rhino, Dagger.
So we're gonna skip over 6.3 for the moment. Yes. Okay. So guys, here's what we're gonna do. I want to introduce you to logistic growth. So please turn to the page that has Katy Perry on it.
Oh,
Seriously?
that's my page.
Okay, so turn to that page. We will come back. There's an intro video for 6.3. If it's for, I don't know, next week sometime. We'll come back around to that for sure. But this is a brand new topic, and I just wanted to like touch on this. In no shape or form are we going to have this just like totally mastered necessarily before we leave here. I just want to give this a touch, and we'll leave it, and we'll come back to it at a later time. But I figure a couple of quick touches is better than one, long chunk of time spent. So here we go. I kind of referenced this earlier with the bunnies, and I said, bunnies, people joke that they multiply exponentially. And the truth is, for a while, it seems like, yes, indeed, they do. Until they start starving, or the eagles figure out where they are, the hawks start swooping in and getting them, right? Or maybe it's just sickness, disease, or lack of food. Who knows? So logistic growth is a more realistic, in fact, very realistic pattern of growth for populations. The growth is limited by what we call the carrying capacity.
Oh my gosh, I remember learning about this.
So I think we talked about this on day 1. We're kind of coming back around to this. So check this out. It's brand new for everybody. If I were to, this is going to be like magic. Watch this.
I love magic.
Are you see that differential equation right there? Please look at it. Look at the differential equation on the screen.
Oh.
What does it look like now?
Exponential.
Doesn't that look like just what we did 5 minutes ago?
Yeah.
It looks just like exponential growth. So the truth is, logistic growth for smaller values of t or p, depending on how you want to look at it, very much looks like exponential growth. So if I put this back in, so this is basically saying that the rate is proportional to the amount present. The rate is proportional to the amount that's there. If I were then to erase all this stuff, I'll do it like this. If I were to erase this, look at it, it's coming back. Do you see it? Well, I want to do that again. That was a cool effect. You ready? I'm going to erase. Whoa, it's so awesome. The P. There we go. It's all better. So if you look at it from this perspective, no longer is it the rate is proportional to the amount that's there. It's a joint variation, right? It's the rate is proportional to the amount that's there times what in the world is 1 minus P over M? Let's talk about the P and the M, and we'll come up with what that is. So P stands for population. So that would be the number of bunnies in the field, the number of people who are sick, if we're talking about a pandemic, or the number of people who have heard the rumor, if we're talking about a rumor spread. Both rumor and pandemic, right?
That's like
It's at the same time. Yes, that's a good point. K is going to be your constant growth factor or your constant decay factor. We're talking about logistic growth, so your constant growth factor. It's the same K as what we were looking at before. Same role here. It's going to control how fast this thing grows. And then M is the carrying capacity. And the carrying capacity is simply a number expressing the maximum number of people that could be in a building, the maximum number of bunnies that could be in a field, the maximum number of people that could hear the rumor, the maximum number of people that could get sick. So for example, there's no way that somebody could look at Valor and say, oh my goodness, 11,000 students at Valor got sick.
Oh, because it's above the carrying capacity.
There's only like 1,200 of you, right? So there's no way 11,000 of you could get sick unless somebody got sick repeatedly lots of times, right? I mean, even that's just silliness. So the carrying capacity expresses how many people actually could hear the rumor, could get sick, so on and so forth. Okay, so population. Would you guys agree with me that based on this, wouldn't population always be less than or equal to the carrying capacity?
Yes.
I use the letter M for max. Does that make sense? Maximum number of people, maximum number of bunnies, whatever. So if P is always less than or equal to M, then P over M would have to be less than or equal to what? Yes. Okay, so P is less than or equal to M. That means that P over M would have to be less than or equal to 1. So then, what about that 1 minus P over M thing? What would that be? So P over M at most is 1, but more than likely going to be less than 1, right? So think about this. 1 minus P over M. Okay, so we're talking about something not present, but I wouldn't say it's an amount. It's a percent not present. There we go. So this is, wouldn't 1, like the 1 in there, wouldn't that represent 100%? Yeah. So that whole factor is the percent not present. And you could adapt this for rumors or sickness. So you could say, if this was sickness, we would say that P is the amount of people, or the number of people that got sick, and then the parentheses would be the percent of people not sick. So think about what happens here when, let's just talk about sickness since it's on our mind from the whole Rock Canyon thing. Early on, if this was going to be the population versus time graph, early on, it's going to look very exponential for small values of time. It's going to grow very quickly. And let's think about why this is. Please think with me here. For small values of t or p, isn't, like when we're talking about like this early phase of the graph, in here when t is small and p is small, won't p over m then be pretty small? Like if, let's just use some numbers to help us. Let's say that it's 1,000 students, and at the start only 1 student was sick. What's P over M? 1 1,000th. And then what's 1 minus 1 1,000th? 999,000, or 99.9%. Right?
Yeah.
Which is almost 1, isn't it? And so if you take exponential growth, which is what I'm putting in the blue brackets, if you take exponential growth times almost 1, what do you essentially have? Exponential growth. However, because it's growth, that P is not going to just stay 1. It's going to become a 2, then a 3, then an 8, then a 12, then a 29, or whatever. So as P starts to get bigger and bigger, this P over M no longer becomes basically 0, like 1 1,000th. It becomes like 300 1,000ths or 500 1,000ths, aka 1/2, and all of a sudden this P over M is getting closer to 1.
Oh, that's where you get the...
Yes, and so as P over M gets closer to 1, wouldn't 1 minus P over M get closer to 0? And what's exponential growth times 0?
0.
0. So that would be 0 growth, wouldn't it? And so as that second factor starts to take over and dominate the growth, the graph of P starts to do this. So P over M is starting to dominate, and now it's really dominating, and now it's really flattening off. It sort of looks like an inverse tangent curve, sort of. You're going to get this horizontal asymptote behavior up there, and it definitely is a horizontal asymptote. What would be the y value for that horizontal asymptote? M. Wouldn't it be the carrying capacity? Our graph of P is never going to get above M because we can't have 2,000 students at Valor get sick. There's no way because there's only 1,200 of you. And so that would limit the growth, and we'd get closer and closer to it. And in practice, we could hit it. But theoretically, with mathematic graphs and all that, we'd never actually hit that.
So I don't know if this question really matters now, but will the inflection point of that graph, will that always be at 50%?
Yes.
Okay.
So you bring up an excellent point. So That's clearly the inflection point, right? Because the graph of P goes from concave up. This is a really good point you bring up. The graph goes from concave up to concave down. This will always happen, always, no matter where you start. This will always happen at m over 2, halfway to the carrying capacity.
All right.
Halfway to the carrying capacity. So if we're talking about Valor and we did have exactly 1,200 students, m over 2 for us would be 600. That's also when the growth curve is the steepest, right? It's right before the 1 minus P over M starts to take over. It's where the graph is steepest. Like you said, it's also the inflection point.
Sweet.
Yes. Okay. We're going to shift gears here in a second, but I want to leave you with this. But before I erase all this, do you have any questions? We'll come back around and, like I said, I am under no illusions that you'll leave here having this perfectly mastered. I think we're laying some good groundwork, but we'll come back around to this for sure. So let's do this. I want to leave you, at least with this part, on a happy note. So when you see that differential equation, and I'll write it up right above. So logistic growth is dp dt equals kp times 1 minus p over m. Let's just try again on that m. There we go. Okay, so if you see that differential equation and it fits that format exactly, then you know that we're talking about a differential equation for logistic growth. The solution curve can be arrived at, don't cry or anything, the solution curve can be arrived at by doing partial fractions. And back in the day when we met, basically what was the equivalent of like every day, I took an entire class period, like all 50 minutes or whatever it was, and we took most of the whole front board and we developed it. Like it would take, if you did it on paper, it takes like pretty much the entire paper to take what I have in blue up there and arrive at what I have down below, that solution curve. It's certainly harder than like eating a bowl of cereal. But it's like, if you can do partial fractions, you can do it, but there's just a lot of things, a lot of moving parts to keep track of. I don't have time to show you that here in our class. If you wanted to explore that, that'd be actually kind of fun to do. It's been a couple of years since I've done that.
Fun.
Here is my point with saying all that. If you see this, then you can be for certain that the solution curve is that. Okay? So the P equals m over 1 plus CE to the negative KT is the solution curve for that differential equation. You remember that curve that I drew up there a second ago that looked like this? Oh, I'll draw it from your perspective. It looked like this. Had like that S shape to it. If you graphed that P equals m over 1 plus C to the negative KT, that's what that would look like. Okay? How are you supposed to remember this? I like mice minus Katie as a way of remembering it. And you have a nice visual here. I'll show you how this is supposed to help. Here is your mice in gray. Do you see it? The one is an I, mice. And then once you do that, then the minus Katie is pretty obvious.
That was creative.
I got this from an old one that was like lice minus licked. It involved like lice, which is gross. And then there was a big picture of a cow with this nasty old tongue sticking out, licked. You know, they used the letter L for the carrying capacity. Anyways, I like mice minus Katie. Far more pleasant than lice and cow tongues. So, anyways, I guess depending on your opinion of Katy Perry, mice. So that's the point there, simply to help you remember mice minus Katie, and you get to where you need to go. Then you'll get some information about the boundary conditions C and K. Not that much different than what we did with the exponential growth and decay, and you're off and running. And we'll do some examples with those. Justin brought up a good point with the whole halfway to the carrying capacity thing. There will be a few other things we'll bring up that will help us with that. All right, we good?
Yeah.
All right, awesome. I'm glad we got to that. So let's do this. I'm gonna.
What's going on?
Not you, my dad. Yeah.
You're my dad.
What about your dad?
You called me Justin.
Are you kidding me?
No.
Darn it!
Judgmental.
I try so hard. I've been doing.
It's all good. It's all good.
I've been
Don't
doing
worry
pretty
about it.
good
Everyone
lately.
does it.
Honestly,
Everyone does it.
let me.
I've been doing pretty good, but that one I didn't even know. Usually I know when I did it. That time I didn't even know it when I did it.
Okay, yeah, Jeff does it a lot.
A lot.
A ton.
A whole lot.
And like even after he told him, he was just like, all right, Justin?
No.
Yeah. Yep.
Okay, so let's go.
We call you? No. Okay,
I'm good.
Justin. Justin. Focus.
It's because they both end in with the and n sound, right?
Yeah, and it's because we look exactly the same.
You look similar and you sound very similar
We
too.
do. We totally do.
And that's not a bad thing. You both have like good, strong
Hey, he's a
voices.
good dude. If I grew up to be something like him, I'm fine with that.
I'm recording this. You should tell him to fast forward to minute 50.
I love you, Dad.
There we go.
You didn't look good.
Let's see here. Let's go with.
Dad, you'll never believe what happened in math class today.
Because they're not the color of the president.
But if you really knew my dad, you knew his name wasn't Justin. Everyone calls him Vanilla Silk.
Yeah.
Yeah, you have heard. Yeah, I've heard of that. Yeah. Vanilla Silk.
No.
Honestly.
Oh my.
Okay, so here's your chance to show that you've remembered.
Let's do
Oh, it's-
that.
we got
Let's
X's
do
involved?
that.
Okay.
That means I should probably sit in my chair the proper way.
So I think I gave you all the information you need.
Don't. I didn't ask. No.
I kept it really similar to the other one. It's a little bit different, but it's.
Oh, is there a plate?
I'm just gonna go.
Oh,
Are you kidding me?
Oh, I can't believe I didn't even like. I just made this up totally off the cuff. X plus Y. No, this is similar to the one in the video.
0.3 or 0.5?
Point. That's a 3.
Okay.
We're supposed to do this.
So please approximate y of 0.3, given that initial condition, differential equation, and step size. We can all kind of compare that final answer, and hopefully we all get a good answer and get the same thing. Since I just made this up, I don't know what the answer is, so we'll just have to work together to figure that out. Birthday boy just left us.
Yeah. So,
He was struggling with
would
it.
you,
Stay
would
away.
you use like this Y and this X? I guess we use this Y and this X.
Yeah, so the one we did together in class, the slope only depended on y.
Mm-hmm.
Since it now becomes an x and y, we'll use the previous points, x and y.
So that's what happened in the intro video, right?
Correct.
Okay.
And it's possible that your differential equation would only depend on x, but if that would be the case, we could put the separate variables. And, we might get separate variables.
For this one, we'll do y0 plus x0. So for y1, we'll do 2 plus 0 to determine the slope. Or would it be
Yeah,
2 plus x?
No, I think you're right on the money. So this is your previous y. Your m is going to be x plus y, so it would be x plus y. So your m would be 2 there.
Okay.
And then you get your step size in there. Yeah.
Alright.
So this is going to start out looking really similar to the one we did together, but then it'll differ after with the second and third.
Wait, which X you use?
Which x do you use? Yeah, so whatever point you're working on, the information you get to get that point, you use the previous point's info to get there. Is anybody in here a programmer type? I've had some pretty phenomenal programmers that have come through here.
Dylan Jessup.
Dylan Justin.
Jake Welch.
Yeah.
Did you see what he did to his room?
No, it's
He's
called
got, no, in his regular room, he's got Christmas lights all the way around and he synced them up to music.
Nice.
So we can just play music and have the lights do the same thing.
That's awesome.
Sick.
That's awesome.
That's fun.
You never got the privilege of knowing Jake, did you?
He was in the other section
Software problems.
last year for you.
No, that's a sad life. Not knowing him.
What'd you get? What'd you
Sad
get?
life not knowing
Is
Jake.
that 0.3?
Weak, Josh.
So I'm not
Did I do that right?
Isn't it
Yeah,
just
the
this?
class does suck.
Yeah.
Except everyone in my class is really good.
Come on.
At least you have that going for you. Yeah.
Everyone in our class is what?
Everyone in our
Except for
class is
Nate.
ugly except for Nate, obviously.
You mean our class, like your senior
Like
class?
the senior class. Wouldn't you guys agree?
Yeah.
mean, we're talking about Nick right here.
You people, okay, well, not everyone, but like the
There's
majority
people in this
of,
class.
okay, but the majority of people in our class are not.
Well, that's like every class.
I have some pretty hot sophomores.
Beauty is in the eye of the beholder.
Yeah, 8 and over.
Oh, yeah.
There we go. All right, so we have about 5 minutes to go here, so let's try to wrap this up. So I don't favor a fancy route here. I like a table because I feel like I can keep a table pretty organized. My x's are going to start at the initial condition and work their way up by tenths. So we'd have these 3 points there in addition to my initial condition. Then y0 would also be part of my initial condition. That would equal 2. And this is where we start to develop our y's. So y1 would be 2 plus, so the slope is based on the differential equation and the previous point. The differential equation is x coordinate plus y coordinate, so this would be 2 plus 0, right? So my slope based on that previous point would be 2 times the step size of 0.1. Are you guys getting 2.2? 2.2, okay. So that's my... Oh, man.
Your self-esteem should be so low right now.
But at least he has some good friends in here to build him up, right? Yes, there we go. Okay, so then y2 would be 2.2. This is where this gets a little bit tougher. Your slope would be based on the x plus y from the previous point. So the x and the y were 0.1 and 2.2. So I'm thinking 2.3 times our step size of 0.1. So this would be 0.23. So I'm getting 2.43. Okay. And then our final step on this journey would be y3. So this would be 2.43 plus... So my slope is going to be 2.43 plus 0.2, so that would be 2.63 times 0.1. So this would be 0.263, so 693. So 2.693. And that'd be that. You guys get the same number I did? Yeah. Okay, good. All right. So kind of a last chance for us to assess where do you stand with this. Probably this is brand new, this Euler's method thing. So odds are pretty good that as you're leaving right now, you're feeling decent about it, but you need practice, don't you? It's brand new. And so make sure you get some good practicing over the coming weeks before we do any assessing on this for real, and you should solidify it. And I'll tell you, if we ever, let me put it like this. This is what I've done in the past classes. If we're ever doing class and we get to the end, so like say right now, and this would be a little short on time, we have like 2 minutes left. But let's say we got to the end of class and we had like 5 minutes and I'm sitting there thinking, man, what do I want to do? Just shout out, let's do a Euler's method. Because you're going to need to get a couple more touches on this to probably get really good at it. And I can just make one up really quick. Hopefully not with x plus y and y 0 equals 2 again, just like this one, like I did. But I'll come up with something a little more original, and then we can practice with that. So I think we're good. Enjoy your fall break. I'll see you on the other side. Thank you.
So
Appreciate
much,
it.
George.
My birthday's over the PSATs. That's gonna be.
Oh, well, happy birthday.